Welcome to our next lecture on IC voltage regulator. In the previous lecture we studied these two topics, 3-terminal positive voltage regulators and 3-terminal negative voltage regulators. In today's lecture we shall take up the next topic, which will be 3-terminal adjustable voltage regulators. The topics given in red color are the topics which we have finished. So, this lecture we will study 3-terminal adjustable voltage regulators. Now, till now we have seen 3-terminal fixed voltage regulators. Those regulators have the advantage that they are simple, reliable, and they require no external components, maybe other than the filter capacitors that you add at the input and the output. But they have the defect that the output voltage is fixed. You cannot change it according to your requirement. But you will have applications where you need to change the output voltage. So for such applications you need to have an adjustable voltage regulator. This adjustable voltage regulator would require external feedback and external components, due to which you can precisely select the output voltage. And these external adjustable voltage regulators also have protections like short circuit and shutdown circuitry, and they need to have access to the reference element, that is the resistor network outside, which gives the feedback to the IC inside. These are some of the commercially available adjustable regulators. This is not an exhaustive list, but just an indicative. And out of this list, the names given here are of negative regulators, rest are of positive regulators. So in our previous lectures we have seen that for a fixed voltage regulator, the feedback resistors R1 and R2, from which the output voltage is feedbacked to the error amplifier, is given outside the IC. Is given inside the IC. Whereas in the case of an adjustable voltage regulator, these resistors are kept outside the IC. So this is a figure of an adjustable voltage regulator, and this resistor R1 and R2, which were inside the IC for the case of a fixed voltage regulator, are now seen here as connected outside the IC. And this resistor R2 is made as a variable resistor. By varying the value of R2, we can change the output voltage. Now the voltage which is developed across this R2 is due to this current IQ and the current which flows from here, which is equal to V regulator divided by R1, that is Ohm's law. So current from this resistor and this current, both of them combine and flow through this, and it forms the voltage across this. Now the output voltage is greater than this voltage, because the output voltage will be the sum of the voltage across both the resistors, and the output voltage is given by this formula. V out is equal to 1 plus R2 by R1 multiplied by V reg plus IQ R2. Now the current through R1 is set at a much higher value than that of IQ, because this IQ value will change according to the change in the load current. It will also change according to the change in the input voltage. So to minimize the effect of these changes in the output, this value is kept at a minimum value, as you can see in the equation here, so that the effect of this on the overall output voltage can be minimized. Now from the definition of line regulation, that is the change in output with respect to the change in input voltage, and load regulation, that is the change in the output voltage with respect to the change in output current, needs to be defined for the 3-terminal adjustable regulator. So let us define that with respect to Vs and IO. So this is the previous equation that we saw for an output voltage. So in order to get line regulation, we differentiate this output voltage with respect to the change in input voltage. So when we differentiate this, 1 plus R2 by R1, which is a constant term, remains as it is. This voltage gets differentiated with the input voltage, plus R2 is a constant term, but IQ is a variable which again gets differentiated with the input voltage. So this term del Vrec by del Vs is the line regulation of the 3-terminal divided by the change in input voltage, and similarly this term is expressed in word here, change in constant current by change in input voltage. Now output resistance, which is nothing but load regulator, and that is calculated using this formula, change in output voltage with respect to change in output current. So this VO we use from the same equation here, and we do the simplification, and we get this as the final equation. Now the total change in the output voltage dVO is given by this equation. Now we can obtain the values of S and RO from the data sheet, and from those values we can find out these values. And now we will take up a numerical to do that. Before we take up the numerical, let us look at a few of the basic things. Now this equation, the previous equation of this output voltage, tells us that this output voltage can be varied by varying the value of these resistors R2 by R1. Now the value of this R2 should be kept larger than R1. But when we increase R2, the value of S and RO would also increase, and due to which the performance of the circuit will go down. This we can see from the previous equation, that when R2 is increased, the value of S and RO is also increased. S and RO. R2 is in the numerator in both the case, so the increase in the value of R2 will increase its value, so it will deteriorate the performance. And if R2 is much greater than R1, then the deterioration is quite considerable. So we have to make a judicious choice or an optimal choice with respect to R1 and R2, and we should choose in such a way that R2 is not made larger than R1. Now this capacitor C1 is optional, it just does the function of filtering. But this capacitor C2 improves its transient response, and this capacitor C3 helps in the rejection of the ripple voltage. So now let us come to our numerical. We have to design an adjustable voltage regulator using a 3-terminal regulator for the following specification. For this specification, our input voltage could be 24 volts plus or minus 5 volts. Output voltage could be from 6 volts to 15 volts, and our output current should be from 0.1 to 1 ampere. And this is the circuit that we will be designing. In this we need to find out the value of R1 and R2. So we choose the ready-made IC MUA 7805. So from the data sheet we know that its line regulation is 5 milliampere for the input voltage varying from 7 to 25 volts. Load regulation is 15 millivolts for the output current ranging from 8 milliampere to 1.5 ampere. IQ is 5 milliampere. Change in IQ with line, that is the input voltage changing from 7 to 25 volts, is 0.8 milliampere, and the change in IQ with load, that is the output current changing from 5 milliampere to 1.5 milliampere, is 0.5 milliampere. So these values we have got from the data sheet. Now we know that the current passing through resistor R1 should be at least 10 times the value of IQ. Now the regulator voltage is 5 volt because 7805, 05 indicates it's a 5 volt. So Vreg is 5 volt. So current through IR1, this resistor is 10 times that of IQ. IQ is given as 5. So 10 times of 5 is 50 milliampere. So we know the voltage here and we know the current here. So the value of R1 is calculated by Ohm's law. So voltage upon current gives you the value of the resistor. So here in our case it is 100 ohms. So after calculating R1, which is a fixed resistor, we need to calculate R2. As you see, R2 is a variable resistor. So we will have to calculate the lower limit of R2 and the upper limit of R2. So we have our output voltage equation given here. So first we will see what is the minimum output voltage given. So here the minimum output voltage is 6 volt. So let us calculate the value of R2 for 6 volt. So in this equation we put V out as 6 volt. The R1 we already calculated as 100 ohms. IQ is given to us as 5 milliampere. We put these values and we do the calculation. And we get the value of R2 as 18 ohms. Now this is the value of R2 for the minimum output voltage of 6 volt. Now let us calculate the value of R2 for the maximum output voltage of 15 volts. So in this equation, instead of 6 we put 15 and we calculate and we get the value of R2 as 181.8 ohms, which is equal to 182 ohms. So the value of R2 should range from 18 ohms to 182 ohms. So commercially available 200 ohms potentiometer can be used in the place of R2. Now let us find the value of S. As seen previously, I have put it here again for easy reference. S is given as this equation, 1 plus R2 by R1. So 1 plus R2 by R1 is here. Change in the regulator voltage 5 volt, which is given in the data sheet, and change in input voltage. So input voltage, our case was from 7 to 25. So that difference is taken, and here you have the change in IQ and the change in input voltage. This input voltage is the same as this, so 25 by 7, and change in IQ, this also we get again from the data sheet, is 0.8 milliampere. So these values are put in this equation and we simplify and we get this value 8.88 into 10 raised to minus 3. Now let us find the value of RO. So the equation for RO is given here, 1 plus R2 by R1. This del Vreg by del IO plus R2 delta IQ by delta IO, differentiation of constant current by output, change in output voltage. So here this value is kept as it is, and these values we have got it from a data sheet values over here. So 1.5 is here, 1.5 ampere and 15 millivolts. So change in output 1.5, 1.5 and 15. We put those values here and we get this sum. So after finding the value of S and R0, using this equation, we find the total change in output voltage, and this is the total change in the output voltage. When I calculated, I got a slight different answer than this, so I have written it here, 88.86, but those are close enough, so that's fine. Thank you.